So last class, right, we saw back propagation, right, and we saw that you could have a deep network and still be able to propagate, propagate the error backwards, and then update the weights, update the bias, and all that. We saw the matrix vector form for doing that. Now there is just one thing that I think I would want to tell, okay, which is about see, right, we haven't yet said said anything about how we take these samples. Okay, so for example, in the last one that we had, I mean, it was, I think, what was it? It was just a mean square error kind of thing, right? So we had like summation yi hat minus yi square, and then we said I going from 1 to 2, and then we scaled it by half, right? Now, ideally, right, you would have several samples. Right? Think of a case where you have images and you want to denoise them. So yi will be like one image, right, and then yi hat will be your estimated image, and then you want to find out the mean square, find out sort of the even square error, right, between the two. And but then you would have to do it over several examples, right? You can't learn with just one example or something. So normally what happens is you'll have something like yi hat minus yi square, and then let's say at I going from 1 to m, and then you can have another summation where let's say right, I mean, so we can say maybe at yij, and then yij, where let's say j is the right, I mean, sort of example number. So you could have like j is equal to 1 to some right, L number of examples, and right, I mean, basically what you might have to do is for every example, right, you might want to and then you might want to scale this by 1 by Lm or something, right, and you would want to make sure that over all the examples you get right, eventually an error which is small enough, right. Now it could be it could be whatever, right? It could be one dimensional, it could be even speech data, whatever it is, right. So what you do is you take, so in a sense, right, you might think that what probably we'll do is we'll push all the examples, and then right before we even do a gradient update, we would want to compute this cost over all the examples, and then once you've accumulated right that kind of an error, then we will update. But then what happens is that becomes too slow a process because of the fact that you may have a million examples, for example, right, and you would have to first of all push all of them through, and then because of the fact that right you've got so many examples out there, even the right movement is not will not be fast enough. So there are kind of right three ways of doing a gradient descent. Only one is typically followed, but then I just thought I'll just talk about it, all three of them, right, what they are. This we could have done before, but right at that time I left it. But I think right now we'll just take one quick look at that. So let's look at the first one, right, which we call batch GD. Right. So this batch gradient descent is like, batch GD is like no. So the entire training set, is used in each iteration, right? That means before you even update. So always, right, let's kind of go back to that to that update equation, which is like whatever your theta t plus 1 or n plus 1, whatever you had, so go to theta t minus alpha, let's say gradient of L, dou L theta with respect to theta, evaluated theta equal to theta 2. Right, this is always the case, but now it looks like, right, this update, okay, which we are going to do, theta could have both your weights and the bias. So the update, right, in batch GD, what will happen is you will actually compute this L theta, right. Here is your L theta, for example, right, this is your L theta. So you compute your L theta over all the examples, okay, but then right, does not you see, right, normally followed, because it is just, you see, right, I mean, even kind of what do you say, computationally you have to do it over a million examples before you even right, make the first update. And the second thing is storage, memory, and also the fact that right, you don't want the movement to be so slow. The other extreme, right, that you can do is what is called a stochastic gradient descent, or SGD, what is called a stochastic gradient descent. Of course, this has also come to be I'll tell you that. I mean, so right now, just kind of take it for granted that we call this stochastic gradient descent, or SGD, and so right here it's the other extreme. So here the weights are updated. The weights are updated. Updated means every iteration. Whenever we say update, we mean after the iteration, after computing gradients for every training sample. After computing gradients for every training sample. That means, so in this equation you will probably take just one example, right? Compute the error, and then update the weights, right? That will be like you have to say, right, iteration. But then this is too oscillatory, because every example, right, will try to take you from here to there, and then right, you won't have sort of a direction, because one guy will swing it one way, another example will swing it the other way. So really this extreme is not something, right, that you would want to use, but yeah, I mean, right, nothing stops you from doing it. The weights are updated after computing gradients for each training example. For each training example. So the drawback of the first one is that right, it's too heavy, right, in the sense that the right inertia is too high. So this is kind of slow. Okay, this can give so kind of right, also, I mean, what do you say, random kind of say directions, right, because the fact that every example will try to swing it in a sort of a different direction. So again, right, not the one that is typically used. So you would not use this typically, right, in any of your implementations. Not use this typically. What you use is what is called mini batch GD, gradient descent. Okay, and this is what we normally use. And in mini batch, right, what we do is, so for example, if you had a basket of examples, then you would actually, right, break them down into these batches, or what is called a mini batch, and and then you would do this loss computation over a batch. So for example, right, suppose let's say suppose you had not that L, right? Suppose you had L examples, and you take M examples in a batch, right? Then the mini batches will be like, you say, L by M, and you traverse, of course, the whole training set, right? You don't leave any example out. You traverse through the whole training set, but at a time you take a mini batch of examples. You can pick the mini batch randomly. Okay, within, I mean, it's not like you have to go in a particular order. You can, but you make sure that you traverse all the examples, right? And within, so you take a mini batch and compute this L theta for that batch. So this L, right, that I wrote here, so that can be, that's not that L. Okay, this L is, well, maybe you can use some other L, I mean, if you wish. So this L and that L are not the same. Okay. Or if you want to treat L as the number of training samples that you are using, okay, then yeah, that's what I have used there for. So this L, I'll just make this as N or something, right, where N is the total number of training samples, and N by M will be the number of mini batches, right. So this will be the number of mini batches, and M is the number of examples in one batch, in one sort of mini batch, right. So therefore M mini, so over M examples you will compute the error, then you will update the gradient, then you will again right, I mean, then you sort of, right, do this in an iterative manner. So of course, many people refer to this mini batch GD also as SGD. Okay, but strictly speaking, one should be using it as mini batch gradient descent. Okay, yeah. So right, this is just an aside, but just to know that because from now on, right, iterations we'll keep kind of talking about iteration, and so on, and therefore when you look at this L theta, right, so you should know that when we talk about an iteration, we are really referring to this mini batch sort of a gradient descent, which means that not all the examples are involved. Okay, in an iteration there is only a mini batch of examples involved, and when you actually cover all the examples, right, so that's called an epoch, right. One epoch is like when you have all the training samples covered. So that's so, right. So that's like one epoch, and normally these networks, right, take several such as epochs to actually train, in the sense that for convergence to occur, it's not like with one epoch, right, you will be able to attain convergence. You will typically require several epochs, and that's where all your computations and all come in, right, whether you have a good processor and so on, how much time you have to wait, right, till you start observing things and so on. But there are certain tricks, right, which you have to do in order to make things move faster. Okay, that is the part on optimization, right. So what basically people do is they don't simply use gradient descent in this form. Okay, this is the most kind of sort of simplest. This is the simplest form for a gradient descent, but what is typically used is not this form. So what you do is, you actually introduce certain things, right? What are all the things, okay, which you would want to do? One is, for example, can you sort of, right, accelerate, in the sense that, if you know that, your slope is rather, let's say, what do you say, very shallow, right? If you have a very, or it's almost like a flat region, right? Now, why would you want to, right, inch at the same rate, right? I mean, when you anticipate, right, that the slope is really less, then you could actually accelerate the way you kind of move forward, right? I mean, it's like saying that I know that this is a flat terrain, so I need not take one small step to get there, right? I might just want to say accelerate. But then it should be such that it's not just applicable for a flat terrain, it should be applicable even in general, so that if I can use a past history in order to move forward faster, I should be able to use that, right? So that is called a momentum based sort of a GD, where a momentum is applied. So when you take the step size, right, there is accompanying with that, there is also a momentum which you give, so that if your the previous sort of a direction and the correct direction are actually aligned, right, then you would take a step, where the previous guy will help you move forward faster, right? I mean, it's like saying that if I had a vector in the original direction which was like this, and if what I'm computing now, if it is also right in the same direction, then if I add the two, right, I'll go faster forward, and it makes sense, right? But the only thing is that when you come near the basin, you could have problems, okay, that we will talk about. But generally, right, it's a smart idea to actually use this as a momentum to actually right, push yourself forward. The other thing is this alpha itself, right, which is sitting there. I mean, so we said that that's a step size, right? Now, this alpha is also something which you can optimize. I mean, so when we say optimization, we really mean tricks that you can employ, right, in order to have a faster way to kind of get there, because otherwise all these things, right, can really slow you down, okay? And these are not that old, by the way, okay? In fact, some of these things are as recent as 2012 and 14 and so on. So that way, in terms of history, right, it's not like, these are like 20 years old or something, and most of them are actually used, okay? So the other thing is about the learning rate. So this alpha is also called the learning rate, right? So the idea is that should you use the same learning rate, or for example, should you have, so for example, right, I mean, if you have, because in this case theta is actually a vector, right? So the idea is that, right, can I kind of fine tune my alpha such that, right, I mean, for let's say, right, certain elements, right, I mean, I can move faster, and for certain, right, I shouldn't, and so on. So this alpha also, right, does not have to be fixed, okay? And alpha is also as a learning factor, right? You can also tune your alpha. Okay, so the idea is that, right, these are the two things that are mainly done with respect to optimization, right, and which we will walk through now. And then there are, say, other aspects which is like regularization that we will talk about later. Regularization is all about being able to make a network learn beyond the training examples that you have learned. That means avoid sort of overfitting. And the other idea behind regularization is that's like having a less complex network. Like I told you, right, what was that to say, razor, Occam's razor, right? So that said that among multiple competing hypotheses, pick the one that is the most simplest, right, and actually explains this one situation. So in the same way, right, if you just allow your weights to be whatever they can be, right, then what can happen is all your weights can come on, and then you will have a bloated network, right, where all weights seem to be active, and then you would actually be, right, overfitting. I mean, it's like saying that, right, I mean, everyone you want them to work. Instead of that, right, you might say that you might want to have a lean network, right, where you say that, no, let me not have all weights act. I mean, you should have a constraint on the weight, right? You should not just, right, let it be unconstrained. Then actually what you can do is, then you can actually regularize, in the sense that you can have a network wherein the weights come up when they have to, right? Otherwise they shouldn't. Okay, so optimization and regularization, these are two things, right, which we should be aware of. Okay, and I hope that we will be able to complete both of them today. Okay, so the first one, right, let me talk about momentum based GD, gradient descent. Okay, so this momentum based GD looks like this. So the weight update equation, right, becomes something like this. So the weight update becomes so I'll first write this, right, then I'll explain what it means. So Vt is equal to, let's say, some gamma Vt minus 1 plus alpha. This alpha is the same alpha, right? And then gradient L theta, theta equal to C theta t, and the actual update is like theta t plus 1 is equal to theta t minus Vt. So, if you see, right, I mean earlier all that you had was this term. If you just replace Vt, right, earlier what you had was this alpha, this one gradient of L theta, but now you have this additional extra term, right, which is this gamma Vt minus 1, and Vt minus 1 in turn would have come from Vt minus 2, and then a gradient of L theta at that particular iteration, right, which will be like theta equal to theta t minus 1, and so on. So, the hope is that right, when you are actually traversing, okay, right, down the curve, instead of taking small steps and trying to get down to this basin. So, the idea is that if you were to add a momentum, right, this factor is actually a momentum. So, the idea is that if let us say Vt minus 1 and this gradient at the current sort of a time step, right, if they are actually both mutually aligned, right, then you would want to sort of add that factor in, right, in order to be able to move forward. Whereas gamma is a number that is typically between 0 to 1. Okay, typically you don't use 1. So, the idea is that it's like right, giving an exponentially decaying weightage to the past Vt's. And as you can see, right, if you try to write, if you start with V0 and let us say write V0 is 0, and then we have like V1 as whatever, right. So, V1 will be a gamma V0 plus something, but that term drops off, you just have the right hand term. Then when you go to V2, right, you'll get like right, gamma V1, and then right, gamma V1 will then actually multiply. So, you'll see that you'll have like gamma square, gamma cube, and so on, right, for the past guys. So, it's like exponentially, because right, when you are here, right, you wouldn't want to give too much importance to what was this direction, right, I mean several steps before, right. So, it's like, so there's actually an exponentially decaying average, right, exponentially decaying average, which actually helps you averaging, right, is what you're doing. Okay, what you're doing is an exponentially weighted, exponentially decaying average. So that the right immediate ones take more are more relevant in order to move forward, and then the past ones, right, have a relatively less role to play. And the idea is that, see, the only problem, right, with this, that I mean this looks like actually a meaningful thing to do, right, because it's like saying, like I said, right, I mean even if they let's say the two are not exactly aligned, still it's okay. I mean but then if the two are exactly aligned, like in a flat surface or something, right, then you could really move much faster. In fact, I mean you could add up all the right earlier steps and really move forward. But the thing is, right, the only problem is somewhere here, right, when you actually come near the which you do not know, right, a priori. So, if you are coming closer to the kind of minima, then so what could happen is you could actually right, overshoot. I mean, because of the fact that you have a previous gamma, right, Vt minus 1, which are going to add to this, and therefore, right, what is typically found, again, right, these are all observations, right. So, when this momentum based GD was implemented, people found that there are oscillations when you come right near the minimum, but otherwise you are very fast. I mean that means that you are able to do your job in much fewer iterations. It's also about how fast you get there, right. So, it's also about involving fewer number of iterations at the end of the day, right. This momentum, what will it do? It will, right, your iterations will become fewer because you are moving faster, right. I mean you are taking larger steps, right, in a sense. Instead of taking baby steps, you are taking larger steps to get there, and therefore, right, you expect that in fewer iterations you will get to where you want to be. But the only thing is, right, when you are kind of hitting, when you are closer to the minimum, so there, right, it can so it is what do you say, it is known to exhibit, so this is known to exhibit oscillatory behavior, known to exhibit oscillations or oscillatory behavior near the minima, or minimum. And but then the point is, right, it is actually used. Okay, there is a variation of this, okay, that actually people use, which is called a Nesterov momentum. I'll just hint as to what it is, okay, because like I said, it, I mean, is there anything else that I have to write here? So, I think let me just write that when Vt minus 1 and delta L theta at theta equal to theta t are well aligned, you get added momentum, and that's why it's called momentum based to move faster, and this is mainly useful in regions with shallow slopes, because that's when okay, you need to go faster, because people write flat regions and so on. It's not just to say, it's not that only for flat regions it's useful. Whenever you have otherwise you will have a gradient which is very small, and therefore your alpha, if it is fixed for some reason, actually it is not fixed, then if you fix it, then your step sizes become really small, So instead of that, you could just use a previous history, It's like using history to accelerate, because you know that, that's how you came, and therefore it makes sense to use your past history. Nesterov momentum, this goes after a person's name, by the way, And do I have the year? I don't know whether I have the year for this one. Nesterov, yeah, 1983. Okay, the guy, his name is some Yuri Nesterov. Okay, so this is some 1983 work. Yeah, this is old, but there is another thing. But there are several other things which are relatively new. So here, what all that he suggests is, because of the fact that you anyway kind of plan to actually make that step forward, which is gamma Vt minus 1. So his idea is that instead of actually evaluating the gradient at theta t, evaluate it at theta t minus gamma Vt minus 1, because you are anyway making that step forward, This is already embedded in your momentum. Therefore, his idea, so to sort of so to explain this, in a sense, what it actually means is that, especially, if you are okay, let's kind of go back to this figure, So what this means is that if you are actually let me choose a different color. So what this means is that if you are here, and then let's say, this is your A point, and from there, you came down to B, okay, and then let's say, you came to C. Now C is where you are sort of, A and B were okay, you are still far away from the minimum, but at C, you are sort of C close. Now this is like, look ahead, look before you leap kind of thing. Okay, that's what this effectively means. Look before you leap, or look ahead prior to leaping. Look before you leap, So what this means is that, so for example, if I had gone the usual way, what basically might have happened is, I would have actually incurred a large step and sort of ended up here. Let's say here is where I end up if I don't use a Nesterov kind of a thing, because all that I do is I have a gamma Vt minus 1, but then my step size becomes so large, that I actually end up on the other side. So by saying looking ahead, let me write down that equation. So this just changes in the following way. So instead of so there's only one change, So Vt is equal to theta. So this all remains the same, gamma Vt minus 1 plus alpha. This is like gradient L theta, except that theta becomes equal to theta t minus what is that, gamma Vt minus 1, So so then what this is saying is, so you can actually go ahead and sense as to what is happening at theta t minus gamma Vt minus 1, and if the slope is already changed, then what will happen is, when you kind of estimate your new Vt, that will actually be a reduced step size, because the sign has changed. Otherwise, you would have left forward to actually D. Okay, see, it doesn't mean that you don't cross over the minima. Okay, that need not. There is no guarantee that for example, you would always. See, the thing is, you want to avoid this jump, You want to make the jump shorter so that you don't end up oscillating. Okay, there is no guarantee that with this, you will always end up like this. But then, if you jump, you will jump much less. For example, you will jump to E and not to D, because of the fact that there is already a change in the sign, and that sign change will reduce the step size which you eventually take. Whereas without that knowledge, you would have already made a kind of big step size. You understand intuitively, what this means, So it's like saying that if I had known that, well, my sign had already changed there, then maybe I would have actually taken a smaller step. I would have gone all the way to D, I would have probably reduced my step size, And that is the idea. Okay, so if you actually implement this, right, people have found that the number of oscillations that you get are far fewer, because it actually helps you know, right, a priori that that you should not have taken a large step, and this is mainly useful when you are actually near a local minimum. The rest of the places it doesn't really matter. Okay, but then when you are near a local minimum, it will help you prevent, you know, undergoing too many oscillations, because oscillations then it means, you know, more iterations and spending more time, right, getting there. You will get there eventually, but then, you know, unless of course, you know, you make steps like the one that I showed last time, that you simply go off the cliff, right. Yeah, so I'm not writing the explanation at all, but I hope, right, you've actually understood, okay, what this means, okay. And this is sometimes also called NAG, okay, it's called Nesterov accelerated gradient, okay. So some people call this as NAG, which is Nesterov accelerated gradient. Okay, this is some 83 work. Then the next thing, right, that we should that I thought we should look at this alpha guy itself. So as far as the momentum is concerned, right, these are the two main things that that one should be aware about.